This lesson is going to be relatively short. We can do an example problem with the sum of consecutive cubes. This is an interesting case because of what it ends up being, and basically what I'm going to do is just practice two more examples of mathematical induction and then leave it to you to solve some more problems with it. I don't need number one here. So this is an interesting result that sometimes when it comes to proving things, you try a couple of things, you come up with a hypothesis, you test it for a few cases, and then you try to make a proof that it ends up being true. The history of this one is that this is how that happened, that we saw that the sum of consecutive cubes was equal to the square of consecutive numbers. So think about what that one means for a minute, that if I took something like 1 cubed plus 2 cubed plus 3 cubed, which would be 1 plus 8 plus 27, or 36, that's the same thing as 1 plus 2 plus 3 squared. Again, an interesting result. Well, we can show that this is true by remembering that the sum of consecutive numbers, n numbers, satisfies the arithmetic sequence formula n over 2 times 1 plus n. If you recall from Algebra 2, that's just the same thing as the average of the number of numbers plus the first and the last. Or if you remember how that worked, 1 plus 2 plus 3 all the way to n minus 1 and n, that I could pair together these and these and these, and I basically have n pairs, or n over 2 pairs. That's how this formula was derived originally. So rewriting this proof, I could say this is the same thing as 1 cubed plus 2 cubed plus 3 cubed plus all the way to n cubed, which is equal to n over 2 times 1 plus n squared. And then I can even manipulate the right side to just be n squared over 4 times 1 plus n quantity squared. So this is just basically redoing the proof a little bit. This is what we're going to be going for, proving that those two are equal with induction. So I'm going to show P of 1, the first case, which is that 1 cubed equals 1 squared over 4 times 1 plus 1 squared. And that's equal to 1/4 times 4, which is equal to 1. So that works. Next, I'm going to show what the P of k case looks like. P of k just means that I substitute k for n, and I'm assuming that 1 cubed plus 2 cubed plus 3 cubed plus all the way to k cubed is equal to k over 2, or sorry, k squared over 4 times 1 plus k quantity squared. And I'll just kind of assume this, and then I'm going to get P of k plus 1, and if I can show P of k plus 1 is true, assuming P of k, then I've got it. Well, P of k plus 1 is 1 cubed plus 2 cubed plus 3 cubed plus all the way to k cubed plus k plus 1 quantity cubed. And I can just do a little substitution of this with this, so that's going to be k squared over 4 times 1 plus k squared times, that would be plus k plus 1 cubed. And if I add them with the least common denominator of 4, I'm going to get k squared times, I'm going to switch this to k plus 1 squared, plus this would be 4 times k plus 1 cubed all over 4. Now if I look at the numerator here, I could factor out the k plus 1 squared, so I'm going to pull out the k plus 1 squared, and I get k squared plus 4 times 1 plus k, or sorry, times k plus 1, my bad, not that it matters, all over 4. And if I really examine this, I can see I've got k squared plus 4k plus 4. You can see that that trinomial is going to factor out into k plus 2 cubed. So k plus 1 squared and k plus 2 squared over 4. So manipulating that down, remember p of k, I'd actually wanted to get that to become k plus 1 squared over 4 times k plus 1 squared. And that's exactly what I have right here. So thus it is shown, and we're done with that. Second example. Let's consider the sequence a sub 0, a sub 1, a sub 2, defined by a sub 0 is equal to 1/4, so the first term is 1/4, and each successive term, a sub n plus 1, is equal to twice the term preceding it, so twice an times 1 minus the term preceding it. And this is for n greater than or equal to 0. So what this is called, when you have something like this, this is called, this is called a recursive formula. It's a formula defined on the previous problem. And one of the challenges sometimes with induction is to find an absolute formula based on a recursive formula. Now for this, we're just going to give it to you. We're going to show that a sub n equals 1 minus 1/2 to the 2 to the n all over 2. Now, finding an absolute formula from a recursive formula can be tedious, but right now we're just focusing on the process of proving it once you've been offered what probably is an absolute formula. So again, let's pause this video for a minute and just make sure you understand kind of what this is gearing towards, or what this is asking. How we have a formula defined on the previous term, and then we've offered a 1. Sometimes you might want to go and say, okay, so if a sub 0 is 1/4, then a sub 1 would be equal to twice 1/4. Actually, you know what? Let's just do the next one. Let's use that here in p of 1. Okay, so we got a sub 0 equals. I'm going to start with a sub 0, then we'll move on to the next term. So a sub 0 is for just the first term. Let's see, that would be. I want to show this, so 1 minus 1/2 to the 2 to the 0 over 2, which is 1 minus 1/2 to the 1 over 2, which is 1/2 over 2, or 1/4. So that's p of 1. Now, just for kicks, we're going to show p of 2. P of 2 in the recursive formula would be a of 1, and a of 1 is 2 times the previous one, so a sub 0 is 1/4, and then 1 minus 1/4, so that's 1/2 times 3/4, which is 3/8. And let's see, p of 3 is a of 2, and the formula was 2 times 3/8 times 5/8. And you can start to see how this is working. A of 3, 2 times, let's see, this is actually 15 30-seconds, so this would be 2 times 15 30-seconds times 17 30-seconds, which is 255 5/12. So if you start to see that there is a pattern here, it makes sense that we should come up with an absolute formula. So again, this is sort of just off to the side so you can see how this is working. We've got the p of 1 case established. Let's show that assume p of k, and p of k means that a of k, oops, let me hold this for a second. Yeah. Okay, a sub k. And you may ask, well, why am I matching k and k here when I didn't match 1 and 0 here? This actually doesn't matter that I didn't match 1 and 0. I could have called that p of 0 and still had it be the first one. It really didn't matter, as long as there's a base case established. So I'll keep these matching here just to kind of not confuse everything too much. That means a of k is equal to 1 minus 1/2 to the 2 to the k over 2. And then my p of k plus 1 is to say, well, in the recursive formula, that would be 2 times a of k times 1 minus a of k, or a sub k. Substituting, that's 2 times 1 minus 1/2 to the 2 to the k over 2, and then 1 minus 1/2, or 1 minus 1 minus 1/2 to the 2 to the k over 2. Well, those 2's cancel, and if I take this right one and let's add those fractions, so I still have 1 minus 1/2 to the 2 to the k, and this would be 2 minus 1 plus 1/2 to the 2 to the k all over 2, just adding those fractions up and distributing the negative. You can kind of see that if I factor the 1/2 out, I'm going to end up with a difference of 2 squares. I'm going to get 1 minus 1/2, and this can get a little bit tricky. 2 to the k plus 2 to the k. So this ends up being 2 to the k plus 2 to the k. And that I can clean up a little bit. I can make that 1 minus 1/2 to the 2 times 2 to the k, which is the same thing as 1 minus 1/2 to the 2 to the k plus 1. Or sorry, I should raise that up as a 2 to the k. There we go. Because this is really 2 to the 1, and if you multiply with the same base, you add the exponents. And that's it. That's kind of what I wanted to show. 1/2, 1 minus 1/2 to the 2 to the k plus 1. And that's done.